Okay, this is the last section of chapter 9. So we're gonna study counting techniques in probability. So today we're gonna learn permutation and combination. You need to know the difference and how to apply those counting techniques in real world situation. So let's think about the fundamental counting principle. In chapter 2, you have learned fundamental counting principle. Okay, so I'm gonna show you the video. Let's suppose there's an event M can occur in M many ways. In M has occurred, an event N can occur. You can see the difference between capital letter and lowercase. So capital letters are the event names, but lowercase is how many ways event M occurs and how many ways event N occurs are written as lowercase m and n. Okay, so we know event M followed by event N can occur M times N many ways. So let's watch this video quickly.
Fundamental counting principle. When two events occur sequentially, and you want to know how many ways there are for these events to occur together, you can use the fundamental counting principle. If event A has M different outcomes, and event B has N different outcomes, then there are N different ways for events A and B to occur together. Suppose there are 2 preferred routes for driving from Boston to New York City, and 3 preferred routes for driving from New York City to Washington, D.C. How many preferred routes are there from Boston to Washington, D.C. via New York City? Using the fundamental counting principle, there are 3 times 2 equals 6 different preferred routes from Boston to Washington, D.C. via New York City.
That makes sense because from Washington DC to New York you have 3 different ways, and from New York City to Boston you have 2 ways. So you can choose this one to go to New York. From there you have 2 other choices. So there's 2 different ways. If you choose this one instead, you still have 2 more ways. So another 2, that makes 4. And for this one you have 2 more choices, so another 2. So in total there are 6 ways. That's same as you choose 3 for the first routes from Washington DC to New York City. Then you have 2 options from New York City to Boston. So you can multiply 3 by 2, right? So going back, there we go. We get to know if there are 2 events that occur in consecutive ways and the first outcome doesn't affect the second one, then we can just multiply them together, right? So here's another example. Consider choosing a president, treasurer, and secretary out of a group of 5 students. So in this, let's say club, there are 5 members, and you are choosing a president, treasurer, and secretary. How many ways to choose a president, treasurer, and secretary? Consider that. So we can think about there are 5 people. Let's suppose A, B, C, D, E are the members. For president, you can have 5 options, right? A can be a president, B can be one, C can be the president, D can be the president, E can be the president. So there are 5 different options. How about for a treasurer? Since one of these people are chosen as president, that person is out for the treasurer because the person who is the president cannot be the treasurer. So let's suppose A is selected as the president, then there are only 4 options. So you can multiply that by 4, right? And for, secretary? Let's suppose B is chosen as treasurer. Then you have only 3 options. So either C, D, or E can be the secretary. So there are 3 options. So in total, 5 times 4 times 3 many ways to choose a president, treasurer, and secretary out of 5 people. So that's total 20 times 3, 60 ways. Okay, that's how you use the fundamental counting principle. Okay, that is the same as permutation. That is the same as permutation. So the permutation of unlike objects, so everybody is different in that group, for example, the arrangement of these things, the things or people in a definite order with no repetition. Okay, so the order matters. I'm re-emphasizing this. The order matters. President, treasurer, secretary, they are all different, right? So the order matters. And there's no repetition for this case. So consider arranging the letters R, A, and T. So when you're arranging these 3 letters, you have 3 choices. For the first letter, you can have R, right? But then second letter can be A or T. So here, you can think about, the tree diagram there. From R, you can have either A or T for the second letter. If you chose A as the second letter, there's no other option. The third letter has to be T because you used R and A. If you chose R as the first letter, T as the second letter instead of A, there's only A left. If you do the same thing for the rest of that, these are the only possible outcomes you can think about arranging these 3 letters R, A, and T. In permutation, order is important. Highlight that. Order is important. Okay, first letter, second letter, third letter, the order matters. And there's no repetition. Determining the number of possible arrangements can be done using the fundamental counting principle. So there are 3 letters, so 3 times. For the first choice, you can choose R, A, or T, so you have 3 choices. So 3 times. For the second letter though, if you have chosen R, then you have only 2 choices. So 2 times, and for the last one, you have only 1 option. Definite number, the left over, times 1. So 3 times 2 times 1. There are 3 times 2 times 1 equals 6 ways to arrange the letters R, A, and T. Therefore, the permutation out of 3, you are using all 3 of these letters to rearrange them. So permute 3 is the same as 6, which is 3 factorial. So let's talk about factorial a little bit here. We just talked about 3 factorial. What does factorial mean? That means you are multiplying all the number that is consecutively lower than 3, starting from 3. So 3, 2, 1. You multiply 3 and 1 less than that and 1 less than that until you reach to 1. Okay, so that is the factorial. 3 times 2 times 1 is 6. So there are 6 manys of ways to count the number of arrangement with these 3 letters. So the permutation is the number counting numbers with order matters, right? And there's no repetition. Remember that order is important and there are no repetition. Excuse me. So let's take a look at this example. Consider how many ways the owner of an ice cream parlor can display 10 flavors in a row along the front of the display case. So consider this example. And you need to ponder that whether the order matters or not. Whether you put strawberry at the beginning or strawberry at the second, it's different. Yes, so the order matters, which means we're gonna use permutation. So first thing that you need to consider is if the order matters. And we can say yes, the order matters. So we know we're gonna use the permutation there. We are using all 10 flavors because we're gonna display all 10 flavors here. So we know we're gonna have 10 factorial, which is 10 times 9 times all the way down to 1. And you get 3,628,800 ways to display the flavors. So we can conclude, using the generalization. If there are n objects, n many objects, then the number of possible ways to arrange all of these is 10 factorial. 10 times, 1 less than that, 1 less than the previous one, all the way to 1. Okay, so here's another example. Consider choosing a president, treasurer, and a secretary out of a group of 5 students again. So the same problem, but we can use permutation here because we understand that now in permutation, the order matters, and we know out of 5, we're gonna permute, we're gonna choose 3 people without repetition. So we can do 5p permutation 3. How do we calculate that? This is how you do it. 5 factorial over 5 minus 3 factorial. If you calculate that, this is 5 factorial and the denominator will be 5 minus 3, which is 2 factorial, right? So 5 factorial over 2 factorial. What's 5 factorial? 5 times 4 times 3 times 2 times 1 over 2 factorial, 2 times 1. And you can see that you can cancel these two out and leaving only 5 times 4 times 3. That's exactly same as we used the fundamental counting theorem in the previous example, right? So let's look at this example again. Consider the set of people in a small club. L, Betty, Carl, and Dan are the club members. For them to elect a president and a secretary, consider whether order is important or not. Yes, order is important because president has to be different from secretary, right? So order is important and there's no repetitions. How many ways are there to elect a committee of 2 in which one person is a president and the other is a secretary? So if you consider to use fundamental counting theorem, we know, let's say president and what did we say? Secretary. There are 4 people, L, Betty, Carl, and Dan. So out of these 4 people, how many ways to choose president? There are 4 people who can be the president. If one of them is chosen, there are only 3 different ways to choose the secretary. So we know that using fundamental counting theorem, there are 12 ways to choose 1 president and 1 secretary out of 4 people. You can also use permutation. This is the same as 4 choose 2 using permutation. That's same as 4 factorial over 4 minus 2 factorial using the formula of the permutation, right? 4 factorial means 4 times 3 times 2 times 1. And 4 minus 2 factorial, 4 minus 2 is 2, so it's 2 factorial, which is 2 times 1. So we know these are cancelled and you have 12 ways. So either way, you're going to have exactly same answer, right? Let's look at another example. So I have all of them here. Number of permutation of 20 objects chosen 3 at a time. So number of permutation, it already tells you it is permutation, right? Permutation of 20 objects chosen 3 at a time. So we're gonna do 20 permutation of 3. So we already know how to calculate this. It's 20 factorial over 20 minus 3 factorial. In this case, in this example, I didn't use real world situation because I want to focus on how to calculate that easily. Okay, so in this case, we know it's 20 factorial over 17 factorial. Well, you can multiply 20, 19, 18, 17, 16, 15, all the way to 1. However, it's too tedious, right? So instead, what we can do here is, we can write it this way. 20 times, 19 times, 18 times, 17 factorial. We can stop here because 17 factorial means it's 17 times, 16 times, 15 times, all the way to 1. The reason why I stopped there is I can cancel these two out because these two numbers are exactly the same thing. So instead of you multiplying all of these numbers all the way to 1, you can just use small partial factorial there and cancel them and have 20 times 19 times 18 instead. Okay, and get whatever the answer is. So I wanted to focus on how to calculate that easily. Okay, so let's talk about this one more time. The generalization of permutation out of n. Let's suppose you are choosing or using the permutation because the order matters. Then you can do n factorial over n minus r factorial. By remembering this, you can easily solve all the permutation problems. And also, I want you to, oops, I went too much. Okay, I also want you to think about this. Recall that n permutation n. So you are using all of the people there, right? Then using the formula, we know n factorial over n minus n factorial. But we also know that we know this is the same as n factorial because when you are using all the people, it's same as n factorial. That means 0 factorial is 1. So remember that 0 factorial is always 1. Okay, 0 factorial is not 0. Okay, I'm saying this again, 0 factorial is 1. Knowing that, we can solve every problem that is related to permutation. Okay, let's solve this problem. A play cast has 9 actors. Find the number of ways the stage manager can arrange the cast if no actor can have more than one role. So there's no repetition and the order matters. Actor A takes role A or actor B takes role A. It's different, right? So we know the order matters and there's no repetition. So we simply can say that, oh, there are 9 let me use this one. Okay, so there are 9 actors and we are rearranging them, but we are arranging all of them, right? So we're gonna have 9 permutation of 9. So that's the same as 9 factorial over 9 minus 9, 0 factorial. We already know 0 factorial is 1, so that's same as 9 factorial. So if you multiply 9 times, 8 times, 7 times, 6 times, all the way to times 2 times 1, you get 362,880 ways. Okay, how about this problem? Find the number of ways choosing 3 initials from English alphabet if none of the letters can be repeated. So we already know that 3 initials. So first name, second name, first name, middle name, last name. The order matters. First name should be different from the middle name, right? So the order matters, and it says there's no alphabet that is repeated. So we know that we're gonna choose 3 using permutation. How many alphabets are there? How many alphabets are there? There are 26 alphabets. So we know out of 26 alphabets, we're using permutation but choosing only 3 letters. First letter for the first name, second letter for the middle name, and the last name's alphabet. So using this, we know we're gonna have 26 factorial divided by 26 minus 3 factorial. So how do we calculate that? We know it's gonna be 26 times 25 times 24 times 23 factorial. I'm gonna stop it here because I know the denominator is also 23 factorial. So we can simply cancel them out and just solve 26 times 25 times 24. And if you use your calculator, you're gonna have the answer of 15,600. Okay. Now we're gonna think about when we have like objects. So let's suppose this specific case. Consider Jordan's collection of 3 identical cat erasers and 2 identical penguin erasers. Jordan wants to display them in a row on her dresser. How many ways of arrangements will be possible? So I'm showing her Jordan's erasers here. Okay, so we know this cat, let's suppose this is cat 1, cat 2, cat 3. Cat 1, cat 2, cat 3, putting it this way, or switching these two, or switching these two, or switching these two, doesn't matter because they are identical, right? Then how can we solve this? Well, we can solve it similarly, but we need to divide the numbers that are calculated twice or 3 times. For penguins, it is calculated twice because if we use this permutation, right? Because these penguin 1, penguin 2 go here, or switching them around doesn't matter. So what we need to do is we can arrange them using permutation first. So we have 5 items or in total, so 5 factorial, right? However, you need to divide that number by the repeated counting. So 3 factorial and 2 factorials are counted twice. So we need to divide them by those 2 numbers, 3 factorial and 2 factorial, okay? So let's talk about that a little bit more. So when you have a permutation of like objects, like the penguins and the cats, the total numbers 10 and factorial over whatever is repeated again and again, you need to divide them by that factorial because they are counted twice. Okay, so let's consider this example. We're gonna find the number of arrangement of the letters of statistics. Okay, so you are given the letters statistics and you're rearranging this. How many letters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we know to arrange these letters, there are 10 factorial ways. However, some of the letters are repeated. So we are counting actually twice twice or more than that, because some letters like S is repeated. It doesn't matter whether you put this S here or put this S there and put that there. It doesn't matter, right? So we need to divide all of the possible repeated number of counting. So for example, S is calculated 3 factorial ways. What other? T is counted 3 factorial ways too. What other letters do you see that is repeated? I see I is identical, so 2 factorial. Anything else? A, C, yeah, nothing else. So this is actually exact number of ways of arranging these letters. So you can have 10 factorial, 10 times, 9 times, 8 times, 7 times, 6 times, 5 times, 4 times. I will stop here as 3 factorial. because I can cancel one of these 3 factorials with that, right? And we know 3 factorial is 3 times 2 times 1, and that's 2 times 2. So instead of these, we can write it 3 times 2 times 2. This is the same as what? 12, but there isn't. So you can either cancel 3 with 9 and 2 with 8, or 2 with 4 and 3 with 6. It doesn't matter, whichever you like to. Okay, so 3 times 3, and that's 2. So you can just calculate 10 times 3 times 2 times 7 times 6 times 5 times 4, and you get 50,400 ways. Okay. Okay, so when it's repeated, you can just divide n factorial over whatever repeated factorial. Okay. So let's move to combination. Reconsider the set of people in a small club are Betty, Carl, and Dan. There are 4 people in this club. Suppose 2-person committee is selected with no chair. So there's no president, secretary, or treasurer. It doesn't matter. We just need to have 2 people as a committee. Okay? So you can already think about, oh, we are talking about the case where the order doesn't matter, right? So in this case, order is not important. So we know that choosing R and Betty as a 2-person committee is the same as choosing Betty and L, right? So AC, R and Carl become 2-person committee is the same as Carl and R. So we can consider we need to, well, these 2 are same thing, these 2 are same thing, these 2 are same thing. So you actually need to divide that by 2. So if we just think about using permutation, we know there are 4 times 3 many ways, right? As 12, but since we have repeated counting, we can divide this by 2. So actually there are 6 many ways to select 2-person committee out of 4 people. So we call that as a combination. The difference between permutation and combination is here. If order matters, we use permutation. Like president, choosing president, vice president, treasurer, secretary. However, when order does not matter, we use combination, like we are choosing committee members. Okay, so here's the hint. The reason why I choose these specific examples for you to remember the cases easily. So if we need to use permutation P, consider the example of choosing president. Both starts with P. If you think if we consider the case where order does not matter, we're going to use a combination, just like when we choose only the committee members. So committee members starts with a C, combination starts with a C as well. So you can easily remember when you can use combination with a good example of choosing committee, and you can think about when you need to use permutation, thinking about the example of choosing president, treasurer, secretary, and so on. Okay? Alright, so let's generalize that. NCR, N choose R using combination is same as N factorial divided by R factorial times N minus R factorial. So without this R factorial, it's the same as permutation, right? But since we need to divide every recount, right? So we need to divide that by R factorial as well. So remember this NCR in this box. That will help you tons. Okay, so shall we look at some examples? Okay, you can just take a look at that. I'm going to explain this a little bit too. Okay, when we are solving some example problems. So let's take a look at this. The Library of Science Book Club offers 3 free books from a list of 42 books. How many possible combinations are there? So let's think about whether order is important or not. You are choosing just 3 books, so order doesn't matter, right? So we know we're gonna use a combination. Out of 42 books, we are choosing 3. Where did my, oh, here. Okay, so out of 42 books, we are choosing 3 books. We are using combination because the order does not matter, right? So that's same as 42 factorial over 3 factorial times 42 minus 3 factorial. So here is easy way to calculate this. Well, I'm gonna stop it here, but I'm gonna write denominator first. We know this is 3 factorial, and 42 minus 3 is what? 39 factorial. So I'm not gonna extend this because I know 42 factorial is 42 times 41 times 40 times 39 factorial. We can stop it here because we can cancel these two out. That makes our life so much easier, right? 42 times 41 times 40 over 3 factorial, which is 3 times 2 or 6, and you can see 6 divides 42 as well, so 7 times 41 times 40 is 11,480. Okay, so we can easily find that. Okay, let's take a look at one more example. At the beginning of the first semester of mathematics class for elementary school teachers, each of the class's 25 students shook hands. Shaking hand problem is very, very common, and it's gonna be in almost every textbook. Okay, how many handshakes took place? So think about it. I shake hands with you. Okay, so between person A and person B, it doesn't matter whether we choose A and B or B and A. So the order doesn't matter. So we automatically get to know it is combination problem because the order doesn't matter. How many people were there? 25. And to shake hands, only 2 people are chosen out of 25. So 25 choose 2 is the solution, right? So we know it's going to be 25 factorial, and we have 2 factorial times 25 minus 2 factorial. To find it easily, we can do 25 times 24 times only 23 factorial because we have 2 factorial, which is same as 2 times 1, which is 2. 25 minus 2 factorial is 23 factorial. So we can cancel these two out. And these two can be simplified to 25 times 12 is 300. That's same as you multiply 25 times 24 and divide it by 2. It doesn't matter. You don't have to simplify it if you don't want to. But I like small numbers, so I like to simplify it. Okay, so you get 300 handshakes. Next example, given a class of 12 girls and 10 boys, you're gonna answer all of this following. Okay, so first problem, in how many ways can a committee of 5 consisting of 3 girls and 2 boys be chosen? So let's think about whether order matters or not. It's a committee, so order doesn't matter. We're gonna use combination, 12 girls and 10 boys. And 5 consisting 3 girls and 2 boys. So let's write that. So there are 12 people, 12 girls, right? And you are, let's say 12 girls and 10 boys. but you are choosing 5 in total, where 3 girls and 2 boys are the committee members. So out of 12 girls, you are choosing 3 girls, and out of 10 boys, you are choosing 2 boys. So that's how many ways you can make the committee of 5 consisting of 3 girls and 2 boys. So how do we calculate this? 12 factorial over 3 factorial times 12 minus 3 factorial times 10 chooses 2. 10 factorial over 2 factorial over 10 minus 2 factorial, or 8 factorial. 10 minus 2 is 8, right? So if you want to calculate that easily, you can do 12 times 11 times 10 times 9 factorial, because we have 9 factorial down here, and you have 3 times 2. So you can simplify that. 3 times 2 is 6. 6 divides 12 with the 2, and you can do the same thing. 10 times 9 times 8 factorial, and I stop there because I have 8 factorial to cancel. 2 factorial 2 times 1 is 2, that's same as 5, and there's no denominator. If you have only any denominator left, that's wrong, because this is how many ways you're gonna have only whole number there. Okay, what's 2 times 11 times 10 times 5 times 9? That is 12 times 11 times 10 is 220, and 5 times 9 is 45. So if you multiply them together, you get 9,900 ways to choose 3 girls and 2 boys as a committee member when you have 12 girls and 10 boys in total. Okay. In the class notes, I have all the solutions there. So if you don't, if you want to go back and solve all the problems again by yourself, you can always go back and check with either video or class notes. Okay. Next example, read the question carefully. It's asking you to find the probability, not the ways, number of ways. This time probability. So to find the probability, you need to consider what is the possible outcome, right? So you need to look at all the sample space, and you need to think about the specific case in this example, right? So to find the probability, let's read this question carefully before we solve the problem. What is the probability that a committee of 5 chosen at random from the class consists of 3 girls and 2 boys? To find the probability, you need to find every cases finding the committee of 5. That will be your denominator, right? What's your numerator? Specific case where your committee is 3 girls and 2 boys. 3 girls and 2 boys we already have found it here, right? So it's gonna be your numerator, but for denominator, you need to think about how many ways can you make committee of 5. So that's same as out of 22 people, you are choosing 5 people as the committee. It doesn't matter whether it is a girl or a boy. Where did I get 22? Because the question was saying there are 12 girls and 10 boys, so there are total 22 kids. So out of 22 kids, you are choosing 5. How do we calculate that? That's 22 factorial over 5 factorial times 22 minus 5 factorial. What is 22 minus 5? That's 17 factorial. Okay, so we can extend 22 factorial as 22, 21, 20, 19, 18, and 17 factorial. You can stop there because we know it's gonna be 17 factorial down here and can be cancelled. 5 factorial is 5 times, 4 times, 3 times, 2 times 1. So 17 factorials are cancelled. What else do you see? 5 and 4, that's 20. So 20 is cancelled. 3 times 2, 6. 6 times 3 is 18. Or you can just multiply all of this, okay, and divide it by product of that. But I like to simplify it. So if you do it this way, it's 22 times 21 times 19 times 3, and you get 26,334. So that's the number of subset. To find the probability of getting a committee of 5 where you can have 3 girls and 2 boys. 3 girls and 2 boys, probability should be something out of 26,334. How many ways can you make the committee with 3 girls and 2 boys? We already calculated it, right? That's 9,900 ways. So that is your numerator. So probability will be this. And if you use your calculator, it's gonna give you approximate number of 0.376 because it's 0.375939 and you can round the nearest thousandth and you get this number. If your number is bigger than 1, it is wrong, because remember, probability has to be always greater than or equal to 1. The maximum probability is 1, the minimum is 1, right? So for the answer for B is about 0.376. Using the same problem, it's continued, okay? Part C is asking you to find how many of the possible committees of 5 have no boys. 5 with no boys. So you still choose 5 committee members out of what? Oops, going the other way. Okay, 5 no boys. That means all 5 are the girls out of 12 girls and 10 boys. So you have 12 girls and 10 boys, right? And this time you have no boys, so all 5 will be chosen from 12 girls. So 12 choose 5, but from 10 you're not gonna choose any. That is same as 12 factorial over 5 factorial times 12 minus 5, 7 factorial, times 10 choose 0. Let's take a look at that. I want you to pay extra attention on that. So we have 0 factorial times 10 minus 0 factorial, which is 10 minus 0 is 10. 10 factorial. We know 0 factorial is 1. 10 factorial over 10 factorial is also 1. 1 over 1. So this part is 1. And think about it. Choosing no boys, that's the only way, right? So 10 choose 0, you can automatically think that is 1. So you can just consider choosing 5 girls. You don't even have to think about choosing any boys there. Okay? Okay, so solving this one, I'm not gonna do all the procedures because by now you need to know, right? If you don't, look at the go back a little bit and you can see how to solve the problems. If you calculate this, you get 792. So there are 792 ways to choose a committee consisting of no boys, just girls. Okay, and let's look at next problems. Next one, part D. What is the probability that a committee of 5 chosen at random from the class consists only of girls? Hey, this time it's asking you to find the probability. that a committee of 5 chosen at random from the class consists only of girls. Only of the girls, we have 792 ways, right? And we already found finding committee member of 5, right? So the probability of no boys should be 790 over total number of having 5 committee members. What was that? 5 committee members. We already found it here. 26,334. $26,334. Then you get approximately 0.03. Okay, so that is the probability for this. Okay. Oh, I already have the number answer there. Okay, I think this is the last one. Almost. I think it is the last one. Okay, given a class of 12 girls and 10 boys, what is the probability that a committee of 5 chosen at random from the class consists at least one boy? Think about at least one boy. And look at my solution there. Why do I subtract the probability of getting committee with no boys? Well, think about the complement of at least one boy. There are several ways to find the probability getting at least one boy. One, you can think about at least one boy means only one boy is a committee member, or 2 boys are committee members, or 3 boys, or 4, or 5. And you can add all of those probability together. That's kind of too much work. So rather than that, you can think about, well, what if it's opposite of that, complement of that part? Committee of no boys. So if there's only a girl, only girls as the committee members, that's complement part of that. So to find the probability consisting at least one boy, you can subtract the complement part, then you get this probability, what we want. Okay, so we can do 1 minus committee of no boy to find at least one boy. Then what is the probability without any boy? We already found it in the previous video, right? We already found that as 0.03. So if you subtract that from 1, we have about 0.97. Yeah, about that. Okay, after this, you need to do the chapter review. There's no video for chapter 9 review, but you will have the opportunity to solve all the problems in chapter 9 review homework in my math lab. It's kind of lengthy, so don't wait until the last minute, okay? Have some time and ponder deeply, and always think about whether you can use the permutation or combination. Okay, so for the permutation, again, you need to think about the order, right? If the order matters, then we use permutation, like choosing president, secretary, if the order doesn't matter, it is a combination, right? Like committee, the order doesn't matter. Okay, I will stop here. Hopefully you guys can have no difficulty solving all the problems in chapter 9 review and homework for section 9 of chapter 4. Chapter 9 section 4. Okay, have a good day. Bye.